I'm okay with this time being taken up by not lecturing. I think that there was some discussion of final project, which is like the last thing that I want to care about. But let's actually like talk about the thing that I had planned for today. That's the implicit function theorem. So, and there was like a sales pitch that I made last time about what the implicit function theorem says, and it comes from implicit differentiation. So, the idea of implicit differentiation is even that. So if you have x squared plus y squared, y plus 1 minus. If you have some equation like that, you can get some relationship between dx and dy. With the intent being, well, like if you treat y as a function of x, you should be able to compute a derivative of y using this information. And that's the idea of the implicit function theorem, but there's something built into it, like this idea of treating y as a function of x. If you look at that graph, is that the graph of a function?
No.
No. But what if you're only allowed to like look in this little box? Is this little box, if you only look in there, does that look like the graph of a function?
Yeah.
Yeah. Yes. But clearly, like, it matters what box I draw. Right, like, you could draw some boxes poorly so that you don't get graphs of functions. For instance, well, I mean, I don't know. What sort of boxes could be bad?
The whole thing.
Yes. So certainly that box is bad. Okay, but there's a point there. Like, if we are allowed to shrink boxes, then maybe we're okay. You could shrink that box down to that little box, and that would now be the graph of a function. Maybe a more relevant example of that is if you start with that box. Like that, what you see in there is not the graph of a function. But could you make that specific box smaller and get graphs of functions? Yeah. Are there any points on the graph where you cannot draw such a box?
Origin.
At the origin, that looks bad. Right, no matter how small a box you draw there, I do not see the graph of the function. I highlight the horizontal line test, vertical line test.
Okay.
Are there any
Can't draw
other?
a box that's a single point. Gotcha.
No, single point is not a box.
Okay.
Right, like this was my convention when I talk about intervals.
Yeah, I know. I just looked at it.
To be, have the assumption A is less than B.
Gotcha.
Which sometimes is annoying because you want to think of like a single point as being a closed interval without getting assigned. Are there any other bad points where you cannot draw such a box?
Vertical tangent line.
I see this box looks bad, and in fact, any box that contains that point is going to have that same badness. So let's just summarize these bad things that can happen. So the first bad thing that can happen is you might just have a box that's too big. In the sense that, well, you can just shrink the box and see it's like two separate graphs of functions that you can think about one at a time. You might have a vertical tangent line. That is, your function might locally look, there's the point you want to look at. The graph might look something like that. Oh, you can't see that. But you know what I was drawing. You might have a picture that looks something like that. Or you might have something really weird going on at that self-crossing point. It looks like there wants to be two tangent lines. But let's actually look at that point and think about what would happen if we tried to like implicitly differentiate this thing. So let's do it. So you would say, well, the derivative of x squared should be like 2x dx. The derivative of this should be y squared minus 2 dy equals 0. So you take that and you go and solve for dy by dx. Like that's all like Calc 1 stuff that you can do, right? What do you get on the left-hand side when you plug in 0, 0?
0 over 0.
0 over 0. So that's like really bad.
Yeah.
That's somehow worse than 1 over 0. But if you notice, both of these had the property that d by dy of x squared minus y squared times y plus 1, the function that we were thinking about, had the property that d by dy equals 0. So that will be the language we'll use. So what does the implicit function theorem? The implicit function theorem says that, well, as long as your box isn't too big, so you're allowed to shrink boxes, and as long as you focus on a point where the derivative with respect to y of the thing you're setting equal to 0, as long as that derivative isn't 0 at that point, then you can find a function which satisfies the equation. You can implicitly find a function. Implicitly as in not explicitly. You know there exists a function, you don't know what it is. And that's what you do when you study implicit differentiation. So implicit differentiation tells you not only can you implicitly talk about this function, but at a specific point you can even explicitly take its derivative. So let's state it. The implicit function theorem says, if you have some function big F defined on an open rectangle, which is differentiable, and you look at some point in that rectangle, such that, well, that point is on the graph of f of xy equals 0, and the tangent line at that point is not vertical, then for any small choice of alpha and beta, so for any like little box that's alpha is supposed to be like the x direction, beta is supposed to be the y direction, there exists some smaller delta x and smaller delta y, and some differentiable function little f, defined on the open interval centered at x of radius delta x, going to the interval centered at y0 of radius delta y, such that the graph of the function f of xy equals 0 is the same as the graph of y equals f of x, where one of those f's was big, the other one was little. So there's all the implicit function. It says if you have the graph of an equation, you can realize it as the graph of a function, at least locally, as long as nothing bad happens. And, well, just like, so let's in order to motivate what's about to happen, when we talked about solving differential equations we found some operator from the space of continuous functions to itself, which was a contraction, and for which the fixed point would solve the differential equation. We'll do the exact same thing here. But the first thing we'll deal with is a continuous function automatically differentiable? No. So, if we look in a space of continuous functions to find the function we want, we better have a separate proof that it's differentiable. Let's do that first. And if you like this lemma 2 is like really the philosophy of what you do when you implicitly differentiate. Right, you assume there's a function, then you play this game to compute the derivative. We'll just justify that. Suppose that big F is a differentiable function that it doesn't have a vertical tangent line at any point. Assume the existence of a continuous function little f from AB to CD satisfying that big F of x comma f of x is equal to 0 for all x in AB. Then I claim that f is differentiable and the derivative is in fact a thing that we can compute. So I guess here are some options. We could figure out, yeah.
Sorry, so in the, I've just momentary lapse. So we have this function that
for f that's a to b cross cd to r, that the implicit function is different depending on what that r outputs, because as you can see clearly there, we have it so that x squared minus y cubed minus y squared is equal to 0. And if we set that equal to 1, then we would have a different graph and those different
Yes.
potential, and thus a different implicit function. Okay, thank you.
Yeah.
Just want to make sure I understand.
Yeah, if you change big F, you'll get a different little f.
Gotcha.
I mean, maybe you can say, well, what if you like continuously change something about the big F? Does that mean that the little f's are going to continuously change somehow?
No, that makes sense. It's just that there was a bit of confusion on my end because, like, we kind of, whenever we do implicit differentiation, we kind of assume the result value of f for these x values and y values. And so I was just making sure that, like, that assumption was like, we had that assumption that, like, if we choose different equals to 0 or equals to 1 value, we're going to get a different implicit function. Okay,
Yep.
thank you.
Yeah. Well, I mean, maybe it could like be a coincidence that these two equations have the exact same
Fair
solutions.
enough. Yeah.
So I want to think about this blank, and there are one of two ways that I want to do this. We can go through the proof and see what just belongs there, or we could put on our Calc 1 brains and see what has to belong there. How many people want to do some Calc 1 for a little bit?
Yeah.
Let's do some Calc 1 for a little bit. So I won't write anything on paper because I mean this won't be a proof. So we haven't like justified treating dy and dx separately and then like dividing by dx. Well, let's try to do it. So you have this function big F of x comma y equals 0, and here we'll like imagine that y is a function of x. So I'll like, well no, that's literally an assumption of the theorem. Let's take the derivative of this with respect to x. What's the derivative of the right-hand side of that equation?
0.
Good.
We'll answer that one.
What do you need to do to take the derivative of the left-hand side?
Change.
Use the chain, the multivariable chain. So this will be, all right, so this is, I have two variables in there, and the whole function takes values in just R. So that means I need to take the derivative of f with respect to the first variable, evaluated at x comma y, times the derivative of x with respect to x. What's the derivative of x with respect to x? Good. Plus d2 f, oh, I didn't do myself enough space, evaluated at x comma y, times y prime of x. That's equal to 0. Do you think we could solve that for y prime of x?
I hope so.
Yeah, so do I. So I guess we should subtract this over and then divide by that. Nice. And wait, did I screw that up? These should be d2 in the order, right? D1 divided by d2?
Yeah.
So do you need another F up top and then the second one?
Yeah. All the more reason that I shouldn't have written it on the paper where people could see. Not that any more people will watch the YouTube video than are in this room right now. So, we know what should go there. It has to be that. Oh, and notice, does it now make sense why we have this assumption that d2 isn't 0?
Yeah.
Negative d2 of f. I think that's how I usually arrange it, right? Like that. X comma, well I guess there it's y, here the function is f. Divided by, no, that's d1, I did it again. Divided by d2 f, x comma f of x. Nice. So, we know the theorem. Let's try to come up with a proof. The proof will, perhaps unsurprisingly, involve the MVT. Of course, we have like three mean value theorems right now. We have the mean value theorem in R1. We have the one variable at a time mean value theorem. And we have the directional derivative mean value theorem. So, Let's try to do it. So let's write down all the assumptions. Let's suppose that big F is differentiable, D2 is not equal to 0. Let's let F be a continuous function with the right domain and codomain, satisfying that big F evaluated at x comma little f of x is always equal to 0. Let's now consider any 2 points, x1 and x2 in the domain. I'm going to try to compute f of x1 minus f of x all over x1 minus x. Because right then I'll take that formula and I'll take the limit as x1 goes to x. That's what I'll try to do. All right, cool. So let's think about this. I claim that it should be obvious that big F of x comma f of x is the same as big F of x1 comma f of x1. Because they're both equal to the same particular thing. What should those both be equal to? Good. That's just this assumption in play. So let's draw a picture of what we can conclude out of that. So we have this function big F that's a map from 2-dimensional space to 1-dimensional space. We have these 2 points, x1 f of x1 and x2 f of x2 in the domain of big F. And I know that they both have the same value for big F. So that's a situation that we can apply the mean value theorem to, I claim. Not just any mean value theorem, but the mean value theorem for directional derivatives. So let's draw the straight line between those 2 points. There it is. So the directional derivative mean value theorem says that I can find some point on that straight line oh, those are mislabeled, aren't they? X comma f of x, x1, f of x1. Midway through revising my notes, I did change notation, so that's why that stuck in my head. So there should be, so if I take there's some point C, and let's look at the vector v, which points from this point to that point. We could normalize it, maybe we should, but it won't make a difference. So the directional derivative mean value theorem says that there exists this point C such that the derivative in the direction of v of big F at C is the same thing as no, minus. Only after I fix the thing that I did wrong. Where maybe you think I should like divide by the distance between those 2 points or something. In fact, yeah, I should, shouldn't I? Let's see. What do you see? What is that number on the right-hand side equal to? 0, because it's 0 minus 0 divided by a number. It's 0. So in fact, we have a point where the directional derivative is 0. And now let's just write down all of the names of things. V, I said, is the vector pointing from x1 f of x1 to x f of x. There it is. Maybe it's even useful to call that delta x comma delta f. Okay, and that's just saying what I already said. There is a point on that straight line where that directional derivative agrees with the average rate of change, which is 0. 0 is equal to that directional derivative. Let's remember the definition of the directional derivative. What's the directional derivative? Maybe by like, well, what did we show that the directional derivative is equal to?
Does it have to do with the sums of the partial derivatives? That's all I know.
Okay, cool. So that is d1 big F at C times v1 plus d2 big F of C times v2. And maybe you even remember that from Calc 2, right? The language for that was nabla F dot V. That is what it is in Calc 3, right? Well, let's see. So that will be d1 big F at C times, what is v1? There's the definition of v there. Yep. x1 minus x plus d2 f of c times v2 is delta f, is f of x1 minus f of x. And remember, all that is equal to 0. It's the directional derivative. We knew independently of this had to be 0. Do you think you could solve that for the difference quotient? Yeah, I don't want to though, so you guys do it and then tell me what to write. Pretty sure you've got space in the version to contain that detail. Should probably be something about d1 over d2. Maybe either based on knowing what the eventual theorem will be. But hopefully the algebra agrees. Is that what people are actually getting in the algebra? Okay. It's like the downside of you guys having the notes is like, I feel like sometimes people just like to like walk ahead in the notes, which is probably a good strategy on your part, but it makes it really hard for me to gauge. Is everyone happy with that bit of algebra? Okay, so I should keep on talking. Okay. So, now remember, we want to compute, so let's actually just quantify this. So this is like for every choice of x and x1, there exists a choice of c, strictly between those two, on the straight line between those 2 points, such that that happens. Now, let's take the limit that we need to take in order to compute the derivative. We need to compute the limit as x1 goes to x of f of x1 minus f of x over x1 minus x. That is to say, the limit as x1 goes to x of negative d1 f of c divided by big F of c, well, d2. And let's even just like wave our hands at the argument for a little bit before I'll write anything down. So let's see, as x approaches x1, what should f of x1 approach? Yes, well maybe I'll even just read it. As x1 approaches x, f of x1 approaches f of x. So then tell me, where should this, so eventually I want to say, well, let's even just jump right to this. That point C, what should that point C be getting close to?
X or x1 or both.
Yes.
Well, it can't be getting too close or close to x1 because this is a point in R2, that's a point in R1.
Oh, x1 or x comma f of x?
Should be getting close to x comma f of x. Nice. Is d1 of big F continuous?
Yeah.
Because this function is differentiable, and that's part of the definition of what it means for a function to be differentiable. Notice when we talked about directional derivatives up there, we can only do that for functions whose derivatives are continuous, whose partial derivatives are continuous. So this is continuous, so what should a big F of C get close to? Sorry, no, what should the actual numerator of that fraction get close to? So that's what So C seems to be getting close to x comma f of x.
We know that f comma f of x is equal to 0. So.
We know that big F of x comma f of x is equal to 0. But it's really important that d2 of big F of that thing isn't 0. So what does the numerator of that fraction get close to? Well, it should get close to this, right?
Oh.
By continuity?
Yeah.
What does the denominator of that fraction get close to?
Not 0.
Not 0 and this. So that like does it, right? Let's just unravel those lines about continuity. As x goes to x1, f of x1 approaches f of x. So x1, f of x1, what point does, so that, those points in R2, what are they getting close to in R2?
X f of x.
X f of x. C is a point strictly between those 2 points. So it should be like even closer. Maybe not by much, but closer. So the point C is also getting close to x f of x. d1f and d2f are continuous, and d2f is never 0 by assumption. So what is this fraction going to have to get close to? D2, yeah, this fraction, but then replace the c's by the things the c's are getting close to?
Yeah.
Yeah. Negative d1f x comma f of x divided by d2f of x comma f of x. Have we just succeeded in computing the derivative of f? Did we get the thing that we said we would? Then the proof is complete. Now, that lemma took a significant amount of time, but hopefully people feel pretty okay about that lemma and its proof now. So, what did that lemma say? That lemma says, as long as we produce a function which satisfies all of the conclusions of the implicit value of the, except for differentiability, then we get differentiability free of charge. Well, but we still have to like produce a function that satisfies all the conclusions of the implicit function theorem except for differentiability. But we have a plan to do that. We'll try to cook up an operator. That operator will be this. And I don't have enough time to make writing that operator on the board offline, because I don't think we'll make terribly much progress from here. So that's like an operator that takes a continuous function of some domain and codomain and gives you a new continuous function of some domain and codomain. So based on your memories from the proof of the existence and uniqueness of solutions to differential equations, Card-Lindelof theorem, you have an idea what I'm going to do. I'm going to pick my domain and codomain so that that thing is a contraction mapping. Once it's a contraction mapping, it'll have a fixed point. What do you think? Will that fixed point satisfy the thing it needs to satisfy? let's just try to walk it out. So let's suppose you have some function for which f of x is equal to t of f of x. Let's suppose we have a fixed point. Well, I have a definition for t of f. It's that. T of f is f of x minus big F of x comma f of x divided by d2 f of x0, y0. So, in looking at this equation, what conclusion can you come up with?
Second thing equals 0.
Second thing equals 0. What's the only way a fraction can be equal to 0?
The top is 0.
The top is 0. So we get the conclusion. Where here I'm relying on the fact that it says informally to be sloppy. So big F of x comma f of x is equal to 0. Aha. But that means something. That means the point x comma f of x, which is an arbitrary point on the graph of little f, is in the graph of big F of x comma y equals 0. Oh, hey, nice. So that at least proves one of the containments that you might want. Right, the graph of little f is now contained in the graph of big F. Yeah.
So why are we dividing by the d2 f x0, y0 at all?
So we are going to, so on the one hand, that operator still does the job. So you're saying, why aren't we dividing by big F of little x comma p of x? That's the question?
Yeah. Yeah, why divide by d2 f in that second term if the fixed point of the operator without that would still apply that?
That certainly is the case. So in some sense, the answer to that question is the proof is easier if that denominator is constant.
Okay.
And maybe that's believable. Denominator being non-constant makes things more complicated generally. And I mean, I don't know, like that's thinking the denominator. Like if d2 big F is continuous, it'll be pretty close to that anyway. And if I allow for that thing in the denominator to be variable, I'll also have to like pay attention to restricting the domain further in order to not accidentally divide by 0 at a point that's like pretty close to x0, y0.
Right.
So
It makes sense to not have a variable, but it, I don't know. I don't understand why we're dividing by the derivative of a randomly chosen point, I guess.
So, I mean, one answer to that question is like, it'll be in the proof.
I guess.
Another answer to that question is when we go and try to prove that that separates a contraction mapping, the fact that we divide by that d2 of big F will be important.
Okay.
And all right, so here's the way that I will want you to answer that question for your own benefit. Write down that the difference that you would need to write down to prove that that's a contraction mapping, and see what the mean value theorem, one variable at a time, tells you, and figure out what needs to be in that denominator for that to have any chance of getting small. And that would still work if you had a variable d2, because it has to, because d2 of x comma f of x is close to d2 of x0, y0. Yeah, I mean, yeah.
But
Well, I'll try to convince you that that was the right, that's the right choice to make on Monday when we actually go through the proof. Cool. So I had promised that on Monday would be like no more lecture, but time to think about final projects and stuff. That is now revealed to be a lie.
The administration's been telling me.
First the dean, now you.